verify the convolution theorem for the Laplace transform for the functions f of t equals t, g of t equals sine of t. Now, convolution theorem states if I take Laplace transform of the convolution of f and g, it's going to be equal to Laplace transform of f times Laplace transform of g. Okay, recall definition of convolution. So the convolution of f and g evaluated at t. It's going to be equal to definite integral. So r goes from 0 to t. Our integrand is going to be f t minus r, g of r, and then we integrate with respect to r. Okay, so here r is our variable. T is going to be treated as a constant. Now, this looks a little strange the first time you come across it, but there's actually a precedent for this in calculus. So the idea is if we take two power series, multiply them together, okay, so the coefficients will be a sub k, b sub m. You're going to get a new power series, we'll call its coefficients c sub n. So the rule for c sub n in terms of the a's and b's is going to be c sub n equals the sum as r goes from 0 to n of a sub n minus r times b sub r. So what we're doing here is we're just lining up the powers so that whenever we multiply, we get the exponent n out. So for instance, we take b0 times a sub n x to the n, b1x times a sub n minus 1 x to the n minus 1, b2x squared, a sub n minus 2 x to the n minus 2, and so on. So our convolution is just taking this formula here and applying it to functions. So the idea is the n turns into our t. Okay, we're summing from r goes from 0 to n. That's going to turn into our integral going from r equals 0 to t. And then a becomes f, b becomes g. So that's where we get our convolution from. Now, let's do our special case. So what I'll have to do is, first I have to compute the convolution of f and g. So first we're going to take f, stick in t minus r. So the function is t, so t minus r is going to come out. And then we have gr, so it's sine of r. We're going to do our integration. So note, for the first part, okay, we're integrating with respect to r, so I can bring this t on the outside after we separate. So we're going to have just antiderivative of sine of r, put t and 0 in, take the difference. Then over here we have to do an integration by parts. Okay, so we separate integration by parts, work it out, that's straightforward. Now, when we do all of our work, what we'll see is, for the convolution, we're going to get out t minus sine of t. If we take the Laplace transform of this function, our convolution, what are we going to get? Laplace transform of t is going to be 1 over s squared. Laplace transform of sine of t, so for sine of at, Laplace transform goes to, okay, it's going to be a over s squared plus a squared. Here we have a equal to 1. So we get 1 over s squared minus 1 over s squared plus 1. It's going to give me 1 over s squared plus 1. If we do them separately, take the product. Laplace transform of t is going to be 1 over s squared. Laplace transform of sine of t, okay, we just saw that's going to be 1 over s squared plus 1. So you'll note, when we work them out in each different way, the answers are going to be the same. So that verifies our convolution theorem in this special case.